In this video, I'd like to show you how to connect an STM32H7 microcontroller to an LCD display using a parallel 8080 style interface. To do so, we're going to be using the flexible memory controller, or the FMC for short, in the STM32H7 microcontroller on this custom designed PCB. I designed this PCB to be a radio transceiver specifically for my micro quadcopter PCB. It has several encoders, 2 joysticks with switches, battery charging circuitry, as well as a CC2500 RF link that I use to communicate with a micro quadcopter PCB. This video will be a start in a series of videos discussing both this entire project, but also in particular graphical design for embedded systems. So in this video, we'll be looking at this low-level interface, connecting the STM32H7 microcontroller to an LCD display, what parameters we have to set up, how do we do the pinout and all of the connections, and start looking at the low-level drivers. But then we'll also move on to designing user interfaces on top of, for example, LVGL, which is a pretty popular embedded systems graphics library. I have made this radio controller PCB design publicly available. If you go to my GitHub profile, either in the link in the description box below or github.com/PMS67, and navigate to the Queen Bee repository, which happens to control the Bumblebee micro quadcopter, you can find the hardware files in this directory, including the native Altium source files for schematic and PCB, as well as the manufacturing files. If you don't happen to have Altium Designer, you can go to pms67.github.io and check out some of the example hardware designs we've seen and will be seeing on this channel. For example, also the Queen Bee controller for the micro quadcopter, which utilizes the Altium A365 online viewer, which is quite a nifty tool. And we can look through the PCB design, we can look through the various layers in the PCB, we can look at the schematic itself, as well as also 3D views of this design if you'd like to interactively follow along. Links in the description as usual. A huge thank you to Altium for sponsoring this video. As we just saw, we can use the Altium 365 capabilities, for example, to share designs for other people to review, to check out, and there are many, many other cool features with Altium Designer and Altium 365. If you'd like to check out these features, please visit the link in the description box below, and you can sign up for an Altium 365 free trial. I'd also like to give a very special thank you to JLCPCB for sponsoring this video. They are the new sponsors of this channel because I do use their services quite a lot, and it seemed like a natural move to partner up with JLCPCB. They provide excellent services for blank PCBs, anywhere up to 32 layers these days, which is pretty incredible, and very, very affordable PCB assembly services that I also used for this Queen Bee radio controller. If you'd like to order PCBs from JLCPCB, you can use their instant quote service, and if you'd like to order the Queen Bee PCBs, as we saw previously, you can navigate to my GitHub repository and download the manufacturing data, and this is all tailored to JLCPCB. The Gerber files, the component placement file, and the bill of material are all for JLCPCB. To give you an idea of the cost of the Queen Bee PCBs, I had 5 manufactured and 2 of them assembled, and this was just around about $100 excluding shipping for the components, PCB, and PCB assembly, which I think is a phenomenal price. Make sure to check out JLCPCB, links in the description box below. There are many, many different types of displays available, and I'm sure we'll cover a few in future videos as well, but for this particular video, I'd like to focus on LCD displays. If we go to a typical distributor, for example Mouser, and check out typical filter parameters, if we'd like to find a display of our own, there are many, many different types available. There are different resolutions, there's different interface types, they can come with touch, capacitive, resistive, or none at all, and they have different methods of driving the backlight. If we just look at, for example, the interface type, we can see there's these various different options of driving or interfacing with an LCD display. There are some things like parallel or MIPI DSI, we could do I2C or SPI, HDMI, and so on. In this particular video, I'd like to focus on parallel type interfaces. For example, this 8-bit parallel we can see here, or any number of these other parallel interfaces. This of course depends entirely on your situation, but I quite like the parallel interface if I have the pins available on my microcontroller because it's quite a quick interface compared to, for example, I2C. If you'd like to learn more about the parallel interface, and this is typically called an 8080 interface, make sure to check out the links in the description box below where I'll leave some information on this particular interface. Essentially, we have a number of parallel pins running from the microcontroller to the display, for example, chip select, reset signals, data, command strobes, write enable, read enable, and importantly also, of course, our data and command signals. And how wide this data command signal is refers to how wide this 8080 interface is. This could be 8 bits, this could be 16 bits. In our case, we will be using a 16-bit wide 8080 interface. The bit width, of course, depends on how many pins you have available, what your display type is, what your display driver is, what color depth you have, what speeds you have, what resolutions, and so on. But pretty common is 16 or 8 bits wide. And this webpage also details read and write cycles, what happens respectively, as we won't be covering this in detail in this video. There are, of course, vendor-specific app notes. For example, AN2790 by ST tells us about TFT LCD interfacing with an FSMC, which is a flexible memory controller, which we'll be doing in this video as well. This happens to be for the STM32 F1 series, but it's quite applicable to many other microcontrollers in the ST family, and also tells you about the various signals involved and their timing diagrams and so on. And this is a very useful read if you haven't worked with these parallel interfaces before. Again, links in the description box below. For the sake of cost, I went with a fairly inexpensive display manufacturer. They happen to be called Waveshare, and if you look at their display section, they've got LCDs of various sizes, OLEDs, e-papers, and so on. I went with LCD displays. Now, if we look at the LCD display section, they do have a number of different displays available with HDMI, if it's parallel, if it's SPI or I2C. What I ended up with is this very inexpensive display, 3.2 inches in diagonal, size, resolution of 320 by 240, and it happens to have touch as well, which we'll look at in a future video. What's important to know before you start incorporating a display into your design is what LCD controller it has, and maybe a touch controller, and also how the backlight is driven. A very common LCD controller that supports I2C, SPI, and the parallel interface is the ILI9341, and this happens to be on this display as well, and this is something you will see quite often. I think it's important to choose a display controller that has quite a lot of documentation. People have used it before because it makes our life a lot easier. We won't have to write the low-level drivers for this. We simply have to take care of the connectivity. We take someone else's low-level driver and we build on top of that. We can see this happens to support an 8080 parallel interface or also SPI. This happens to have this standard 2.54mm pitch header as a mount, where I have a female head on my board that simply plugs in, and I have those 4 mounting holes. And then we have all these various connections. For example, the power supply connections, power and ground. We have our 16-bit wide data bus, the signaling we saw before, chip select, data command strobes, and so on. But also we have backlight connections, and this happens to have a touch interface as well. So depending on how you want to set this up, from what voltage you're driving your display, you will of course have to adjust your schematic. They do also have a wiki page, which tells you more about the display details, as well as the ILI9341 display driver IC, which gives you again more information on its functionality and how they've wired it up and how you should wire it up in your design. But we'll jump over and look at the schematic in just a second. I'll also leave a link to the ILI9341 datasheet in the description box below in case you're interested. It is quite a long document at about 250 pages, but if you really want to know about this IC and what it's capable of, make sure to check that out. We won't be needing terribly much of this because it's typically incorporated already for us on most displays. Looking briefly at the hardware design to familiarize ourselves how you might set this up on your own custom hardware design or PCB. For this particular Waveshare display, I've just followed their form factor, so I've got the relevant opposite gender connector, so this female 2.54mm pitch header, along with the 4 mounting holes around the perimeter that Waveshare specified in their mechanical drawing. The pinout of this connector we can see here, I've then just taken from, again, the Waveshare documentation, and typically displays will not have this type of DuPont style header, but rather will have a flex cable or FFC attachment, so be wary of that, but all you have to do is follow that pinout. That is then simply routed directly over to the microcontroller to its relevant pins. We'll come back to that in just a second. On the schematic, this happens to be the display connector pin out. I've given myself some options in terms of a variant if I want to supply the display with 3 volts or whatever the system voltage is, and how I want to drive the backlight with these various jumper resistors. So if we go into the variant view, we can see, of course, not all of them are placed, so we don't actually have shorts there. But this is the pinout from Waveshare, again, very straightforward, and all I'm doing is a point-to-point connection to my STM32H7 43 microcontroller. And we'll see how we can get this pinout in just a second when we go over to CubeIDE. Before that, I want to quickly say why I chose this H7 microcontroller. Now, it's probably quite a bit overkill for this design, but the reason I chose it was because it has an FMC, which is a flexible memory controller, which we need to drive this parallel 8080 interface. It has enough pins, so this is quite a large, over 160 pin package. It was fairly inexpensive at JLCPCB, around $4 or $5, and cost really isn't an objective for this design anyway, but it's still very cheap and powerful enough to handle the UI, the control requirements of the system, and has plenty of power to spare. But also importantly, in graphical applications, it needs to have quite a bit of memory for example, the display buffers. If you're doing single or double buffering or anything else, you will have to have enough RAM, but also enough flash to store, for example, images. And this part on its own has quite a large amount of flash and RAM, which is sufficient for my needs in this particular application. In some situations, however, you might need external, for example, QSPI flash memory, and maybe even external RAM to hold the memory buffers. Now, this display itself is 320 by 240 in resolution with a 16-bit color depth, which is small enough to fit in the RAM, even with a double buffer for this STM32H7 microcontroller. I didn't have to attach additional SD RAM or external flash to hold whatever information I need to hold with this interface. But this is something important to keep in mind for your applications. Oftentimes you will need additional external memory. But in any case, all I'm doing is a simple point-to-point connection. I don't really have any series termination or anything between these display headers and connectors. I'm just following whatever Waveshare had suggested in terms of pull-ups, pull-downs, decoupling, and so on. But essentially, these are just point-to-point connections. Another point to mention with this specific display, and also a reason why I chose it, is that it simply needs a 3 or up to 5 volt connection to power the backlight. And then actually to control the backlight brightness, all I'm using on the STM32H7 is a PWM generated by a timer. This way, at a duty cycle of 0, the backlight is pretty much completely off, and the highest brightness is achieved at a duty cycle at 100%, and it can vary anywhere in between. Typically, for most displays, however, you will need to have an additional, for example, boost or LED driver to drive the LED strings in the backlight of the display, which require additional components, additional feedback complexity, and so on. And another reason why I chose this fairly simple display, I can simply provide power to the backlight driving circuitry and then a PWM signal to vary the brightness. But keep this in mind as well. And these point-to-point connections you can see here on the STM32H7 microcontroller, we can see this kind of brown yellowish color are all of the display connections, and they're mapped all the way around the microcontroller. Their pin positions are relatively fixed, as we'll see in just a second, and all I'm doing is point-to-point connections. Of course, trying to keep them as short as I can, reasonably, spacing them out, as we can see here, and not adding extra additional length. But I'm doing no length or delay matching whatsoever. Simple point-to-point connections, and that's absolutely fine. So with this very, very brief overview, let's jump over to STM32 CubeIDE and see how we can set up the FMC to interface with our display. We've now moved over to STM32 CubeIDE. I've created a new blank project and selected the STM32H7 IIT6, which is the microcontroller I'm using in this particular design. We have to, of course, set up the usual basics, that is the clock, that is our debug method, if that's JTAG or serial wire debug. We need to set up a backlight timer, and of course, predominantly the flexible memory controller, which is part of this H7 microcontroller, or the FMC for short. The FMC will handle the low-level communication between our microcontroller and the display, and vice versa. And this will emulate our 8080 parallel bus. Essentially, you can think of the FMC as a memory mapped interface. We're simply going to write and read from certain addresses in memory, and this is how, on the low level, it then communicates with the display, very simply speaking. As a basic setup, I'm going to set up my clock first. In terms of clocking, I have this external CMOS oscillator at 26 MHz fed into pin PH0. So I can either go to the RCC section and just enable, and then go to HSE and click bypass clock source, and that will just enable a single input on PH0. Under sys, then scrolling down on the left-hand side, I'm going to go to trace and debug, click on debug and enable serial wire, but also with a asynchronous trace output, because that's what I have on my particular board. And just like that, we have our 3 serial wire debug pins and my MON crystal oscillator input, and we'll do the clock configuration just a bit later, because we have to adjust our clocks based on our input frequency. If you have different display types, you might go on the left-hand side to connectivity and, for example, select I2C or SPI. Or if you've gone a bit more fancy, you might have gone with an LTDC RGB type interface, which you can on certain microcontrollers select under multimedia. For us, however, and because luckily this H7 has an FMC controller, this is typically found under connectivity. So on the left-hand side, I'll click on FMC, and we can see already a few options in this second column here. Typically an FMC we might use to hook up to an SDRAM, so an external random access memory, or maybe even NAND flash or NOR flash or something else. But we can see here that we can also connect to various LCD displays. I'll just be selecting this first bank, so LCD1, the first display, and this section is what we're going to be using to figure out what the pinout is of this STM32H7 microcontroller. Of course, we could go through the datasheet and manually try to figure out where all of these various pins are mapped, but I just find it much simpler, much quicker to go through CubeIDE and just follow this general process. There is a tiny bit of flexibility when setting up this FMC, if that's for SDRAM or for LCD displays, as we'll see here. So for example, just to remind ourselves, looking at a random website for this 8080 interface, we have a few signals we have to set up. For example, the chip select, there might be a reset signal, data command, write address, write strobe, read strobe, and our parallel data bus. So let's keep that in the back of our minds. Going back to CubeIDE, the chip select, we have various different options, and this is just simply to make your routing life easy on the PCB. So if I select any one, this is the chip select pin, it puts on PC7. If I click on a pin, we can see at the top of the microcontroller, we now see a pin flashing. So we could also select PD7 to be our FMC chip select pin. So this depends on what makes it easier for you to route, otherwise there's not particularly much difference. I'm just going to go with this chip select any one. Our memory type is actually going to be an LCD interface, and this already enables a few other pins. Now, unfortunately, the terminology between the 8080 interface is different if you look at STM32, if you look at the display vendors. So here we have NWE, which is the N stands for inverted logic, and WE is write enable, and NOE stands for inverted output enable, which is actually the read enable pin. So you have to do a tiny bit of mapping between the different names people give to the same pin or signal types. Then we have the register select. Now, this register select actually means the data or command signal. This is the one we see here, this D/C. So if this pin is pulled low, we're sending a command. If this pin is pulled high, we're sending data. Now, unfortunately, this has an unfortunate name, register select, so we can select a pin that is free and which helps us best with routing. So you can go anywhere from A0 to A25. I happen to have gone with A16, which is my register select, which is on the right-hand side of PD11. Now, it really doesn't matter where this sits, as long as it aids your routing, but we do need to remember this because this will change a bit in our firmware, which we need to remember later on. Again, register select maps to the data command signal. Then we have the data selection, and for us we can do either 8 or 16 bits, and we want to utilize the full 16 bits because we have a maximally capable 16-bit interface. So I'll select that, and we can see a lot of other pins appear here. Now, a lot of these pins might be pretty inflexible, so we can try, for example, control clicking on one, and we can see, yeah, this is the only place this data 1 pin can be. Let's try a different one. A lot of these pins are pretty static in their positions, and also spread quite typically across the IC itself. So I would use CubeIDE to get this mapping for me, and then I would transfer this from CubeIDE back to my ECAD tool, in my case Altium Designer. That's simply what I've done. All of these signals here, the LCD dot signals, are all taken from CubeIDE from their fixed or pretty much fixed mapping. We do have to take care though, we've done the FMC part for now, at least just figuring out the pinout, but we do also have other signals typically, for example the reset signal, which is simply tied to a GPIO of the microcontroller, and we can see here this is active low, so it's inverted logic reset signal. And of course, we also have the backlight brightness adjustment, which is simply a PWM. This could be running at 20, 30 kilohertz, and we control the duty cycle of that PWM signal to adjust the backlight. And remember, this depends on the display you're using. Oftentimes, you'll have to implement your own backlight driving circuitry because that might not be included on the display you've acquired. Oftentimes, it isn't. So in that way, that's all I've done here. The reset signal I've just mapped to a free I/O. The backlight PWM, I've set up a timer channel, which we'll see in just a second, and the rest I've done simply via following the FMC setup in CubeIDE as we've just seen. The powers I've taken from the WaveShare datasheets and references, and this also happens to include this touch controller, so this TCH signals. Ignore them for now, we'll deal with that in a future video. So looking at the final pinout then, I've moved to my main project where I've also added in various other peripherals, but I've followed exactly the same procedure, gone to connectivity, set off the FMC, and chose the relevant settings as we've just seen before. But of course, we can't forget, I've also set up the clock. Now keep in mind, there isn't actually a physical clock connected from our microcontroller to the display, but the FMC controller within the STM32H7 has its own clock or core clock as well, which we can set here. I've simply set to a reasonable 100 megahertz, which will be important for timing calculations in just a second as well. In terms of the backlight PWM signal, I've mapped that to a relevant free timer channel. We can see that's on PA7 here, timer 14 channel 1, and let's just quickly look at the config for that. I've set it to active, and I've set simply the channel to be PWM generation channel 1 with a prescaler of 120 and a counter period of 100. If we go to clock configuration, we can see all of the timer clocks have a core of 240 megahertz, so we need to divide that down to be around 20-30 kilohertz, and I'm using the prescaler and the counter period to do that. So the core frequency divided by the prescaler divided by the counter period is the frequency of my timer. And then I can simply set my timer register anywhere between 0 and 99 to vary my duty cycle of this PWM. And this is quite a simple application of the timer where I can control my backlight. Now that we've figured out how to do a pinout for an FMC controller, and as you can see, that's very, very straightforward, nothing fancy involved, there are also a couple options within the FMC controller. For example, we've already selected the memory type, but we can also sometimes select different banks if we enable the FIFO or write operations and so on, and we leave them for default typically. However, we do oftentimes have to adjust the timing also for our 8080 interface. So we have this address setup time in H clock cycles, data setup time in H clock cycles, and bus turnaround time in H clock cycles. This depends on not the display, but it depends on the display driver. So in our case, the ILI9341. The H clock cycles refers to the clock we saw previously in the clock configuration, which is this FMC. So I've designed this to run at 100 megahertz clock. So actually one of these clock cycles is 10 nanoseconds because we're running that off 100 megahertz clock. And that's why this FMC clock is important. In terms of calculating these parameters, why are they 3, 2, and 2? All I've done is followed application note AN2790, which we saw towards the start of this video, calculating the FSMC or FMC timings. And for this, we have various different equations. These equations refer to, for example, the H clock, which we just saw as well, but also these other parameters here, such as TCYC, TCYC read, and so on. And we take that from the datasheet of the relevant display driver. Following the ILI9341 datasheet and scrolling pretty far down, we can see they have timing characteristics for our 8080 type interface. And from this, we can pick out the various parameters we need for these equations. So for example, the write cycle time and so on, or the write data setup time, I would use these parameters, which this AN2790 refers to, and simply plug them into the relevant equations here. And that's then how I came up with the address setup time, data setup time, and bus setup time being 3, 2, 2, and these are expressed in terms of H clock cycles. Now I'd like to leave that as an exercise to you to follow that ILI9341 datasheet as well as the AN2790 application note. See for example, the ILI9341, if you get the same numbers, or for a different interface, what numbers you would get. But that's pretty much all we have to do for this basic configuration. So now I've let STM32 CubeIDE generate the code automatically from our very bare bones project we created just earlier. So we have our main.c here, and before we actually control anything with FMC or add in drivers, what we want to do is first of all toggle the reset on our dedicated GPIO reset pin, and also start the backlight timer, and we'll just set the backlight to, let's say, half the brightness. So scrolling down after all the peripherals have been initialized, I'm just going to paste in some code, and all I'm doing is simply setting the reset pin low because it's inverted logic. Then I'm waiting 50 milliseconds, setting the reset pin high and waiting 50 milliseconds. A tiny delay is oftentimes favorable. 50 milliseconds might be too much, but it's safe enough. So we toggle the reset pin, and then what I want to do is also start my PWM timer, calling the HAL function, passing in my struct. In this case, it's timer 14, timer channel 1. We saw the setup earlier, and then I'm simply setting the capture compare register to 50 because we defined our duty cycle from about 0 to 100, 0 to 99. So it's about halfway. I've uploaded the code to the board via serial debug. I'm powering it currently just via the battery attached. And here's a pretty boring picture of what this looks like. We simply have a fairly inactive display that we've toggled the reset, and we've set the backlight brightness to 50%. So not terribly much to see here. I'll make a video once we actually get some action, so to speak, on the screen. Now to actually get to the interesting part where we want to connect up to the ILI9341 driver IC, we have a few different options available. One is we scan through this 250-page datasheet and try and write a driver ourselves, or we could not try to reinvent the wheel for something as fairly complicated as this and use many other people's implementations that are readily and freely available. And I must say I currently prefer the second option, although it is interesting to know how, for example, this ILI9341 is driven and how this works. For this, there are of course many implementations available. The one I've stumbled across, which I quite like, is by Andriy Honcharenko, if I'm pronouncing that correctly, and he's written quite a few different libraries specifically for STM32, but also for, importantly, our driver IC, the ILI9341. So we'll be basing our tests or our low-level drivers on their work. So if we look at the source file here, we can see he has the ILI9341 driver, as well as some examples, as well as some fonts, which we can then use in combination with that driver. So what I've done, I've simply created in my source directory another folder called display and copied and pasted all relevant files in. That includes the ILI9341 drivers, some various font, color, and register defines, and we can use that as a starting point and try and tie that into our code, at least to give us a baseline to test if our functionality and connectivity is working correctly. Then in future videos, we will be building on top of this low-level driver, for example, to add in LVGL or TouchGFX and so on. But this is typically the workflow I do when I try to implement displays in embedded systems. So before including the ILI9341 drivers, let's see what actually is contained in those. So if I go to the .h file, on the right-hand side, we can see the outline of this .h file. We can see we have initialization functions, test functions, which will be very useful for us, drawing functions, such as the low-level drawing pixels, drawing circles, and so on, and also draw image functions, which will then be used by a higher-level graphics library, such as LVGL. There are some other commands as well, for example, turning on color inversion, turning on backlights on and off, and so on, which are all very, very useful, and luckily we don't have to write this again. The .c file that accompanies this is quite a lengthy bit of code and is essentially taking, for example, these commands such as write data commands, write data and write commands from the datasheet definitions and their registers. Before we actually use these functions, the way actually the FMC is being utilized by this library, we need to remember that the FMC is effectively a memory mapped system. If we write or read from a certain address space in memory that corresponds to the FMC memory, we are through that writing or reading from the display or this parallel interface, and that's exactly what is being exploited here. We seem to have two base addresses, one at this hex address and the other base address at this hex address, and then the writer of this driver has defined various macros that simply accesses those addresses based on what command or what data we write or read from it. So for example, the command write, which takes as an argument command, is simply accessing the LCD base 0 address, which was defined up here. Now, if you want to write a data, all we're accessing is then simply a different memory space. And this is how the FMC is actually memory mapped. We have one memory region for commands and one memory region for data. And then we simply have these macros to access those and make that a tiny bit neater. The question is, however, where do we even get these memory addresses from? Why is this hex 6 followed by 7 zeros, and why is this data section shifted? And this depends on the microcontroller you're using and its address space, and also how you set up the FMC. The way we can find the base address of the peripheral is by looking at the relevant reference manual. For the STM32H7 series, we have the reference manual RM0433, and if we jump down to page 800 of this 3,500 page document, we can see the external device address mapping, and this is for the FMC. So scrolling down to figure 98, we can see we have a start address of hex 6 followed by 7 zeros, all the way down to hex D followed by 7 Fs. Now, depending on what peripheral we're using, if we're using SDRAM, or if we're using SDRAM Bank 1 or Bank 2, or if we're using NAND flash and so on, we have different start and end addresses. Because what we selected in CubeIDE, that is, we selected the first LCD instance here, that means we are actually starting from this NOR PSRAM SRAM bank, so Bank 1. And this happens to be the start address of hex 6 followed by 7 zeros. And it should now come to no surprise as why this is now LCD base 0. So hex 6 followed by 7 zeros taken from the reference manual, taken from the FMC section, and this is because how we set it up also in CubeIDE, which part of FMC we're using. This is great, and this defines the base of where we can send commands. But if we actually want to send data, we have to use this second address, which has this offset. So we have the base address, but we have this hex 1000 offset for writing data. And this refers back to when we set up in the FMC, when we selected our register select. Remember, we could select a register select from A0 all the way to A25. And for the sake of routing, I chose A16. And this register select is actually the data command strobe as we saw in the schematic, and this is referring to what we've already covered earlier. So this data command strobe, if this is low or high, will change between command or data writes on reads, and this is toggled by, in our case here, register select A16. And this will then change in turn this base offset. And here's an image that can explain this mapping. And I've taken this image thanks to Controllers Tech, and I'd strongly suggest checking out their YouTube channel. They've got some great videos on STM32 microcontrollers and interfacing with various peripherals. I'll leave a link to them in the description box below. But they shared this image, which tells us how the selection of the register select, so this data command strobe pin, changes the offset. So depending on which register select you set in the FMC config, you have to change this hex base address. So in our case, we set A16. That means we are changing this section of 4 bits. So A16 is essentially a 2 here. So we get hex 60020000 as our mapping. So therefore, this shouldn't be a 1. Rather, we should change this to 2, again, based on that image and that mapping we saw. This would pretty much be the end of the story. We could then simply tie in the ILI9341 header and select our init function and then, for example, fill the display with red, green, blue, or whatever color we want. However, there's a bit of a quirk with this particular microcontroller, the 8743II, and we can go to a forum post to see what is actually happening. And this also happened on my end. I couldn't get the read writes to work, anything proper to show on the display. And their solution here was actually to do a memory swap configuration. Rather than accessing hex 6 followed by 7 zeros, they remapped this memory bank to hex C followed by 7 zeros because of some issues of the CPU actually messing with that memory region and rearranging, which causes, of course, this whole implementation to fail. So what we can do is call this HAL memory swap function and then simply change our base address from hex 6 followed by 7 zeros to hex C followed by 7 zeros. And that's exactly what I did, and that happened to solve the issue. And again, looking at the reference manual, we can see the hex C start address is actually a remap of FMC NOR PSRAM Bank 1, which is exactly what we're doing to solve this issue. And we're still keeping this 2 offset here because we're still using, of course, the same register select pin. Then in main.c, I will add in this set FMC memory swap config from the user forum post to make sure we're accessing the right bank now. I believe you can also set this in the pinout and configuration under FMC bank mapping in the FMC configuration section, but I've just left it by calling this function here. Now to tie in the driver, I'm simply going to include the header file, see if this compiles. After we've done the memory swap config, we've toggled the reset, we've started the backlight. I'm going to call the LCD init function, which is defined in the ILI9341 driver, and I'm going to call the test function and see what that does. Then build and run, and this will flash this to the ST microcontroller. And this is the result of this code now being uploaded, and this is the exact test pattern we are meant to be seeing, which is essentially just a collection or columns of colored stripes indicating that our ILI9341 connection is working and we've included the driver correctly and also mapped our peripheral correctly based on this FMC config. Now, of course, this isn't terribly exciting. Maybe we can also test out the other functions such as drawing an image or drawing circles and text and so on. But now we've verified the very basics of this driver and this interface. With all of this mapping now in place, what we also do have to take care of is, of course, the display width and height, that the driver is aware of this, but also the orientation of the display. Now, scrolling down in the ILI9341.h file, we can see defines for the pixel width and height, and this is of an orientation of typically portrait. So that's why my pixel width is 240 and my pixel height is 320. And then we use an orientation command to then rotate our image. And here we can scroll down and we can see we have portrait, landscape, portrait mirror, and landscape mirror modes. On the right-hand side, there is a set orientation function, which we then use those defines after we initialize the LCD to set our orientation, and then the driver will take care of everything else. So what we need to call is the LCD initialization function, the set orientation function, and then we'll just write some very, very basic test code. For example, filling the display with just a single color, but also we can draw an image. After our memory swap config, after toggling our GPIO pin for the reset, and after starting the backlight, let's say at an arbitrary value of 50%, I'm going to paste in LCD init and a call to LCD set orientation. And in my particular case, the way the PCB is mounted, the way the display is mounted, I need LCD orientation landscape mirror. Then in just an endless while loop, I'm going to fill the RGB with a single color, let's just say a color of green, which was defined in the colors.h header file. I'm going to wait half a second, fill it with a color of red, and then wait half a second again. And then I'm going to call the LCD draw image function, which takes an X and a Y position, as well as the binary data of the image. Now, there are previous defines for this image data, and I've just taken that from one of these drivers. I have an array which contains my binary data of the image, and I'll show you in just a second how to generate that. And it contains a struct which tells you about the image dimensions, in my case 320 wide, 240 high, It's got 640 bytes per line, and the color bit depth is 16 bits, and we're assigning a pointer to the picture data, which is just an array to this binary data. And that struct then needs to be passed to the driver to the LCD draw image function. To actually generate this raw binary data, there are of course many different options online. I just typed in online picture to array, and I believe this file to C style array converter is pretty good. I can choose a file. For example, I've just chosen the Phil's Lab logo. I can choose the code format, and I just want it to be in hex, for example, and I can choose the bit depth, and what we're using is 16-bit RGB. If you want to resize, we can do that here. We want little endian, and we can choose the data type and so on. And then the result is shown at the bottom. I've resized the image, that's why it looks a bit wonky, but that's simply the array. Then I would copy over into this particular demo, and that's all I've done here. I have used a different image. So what I'm going to do is I'm just going to upload this code. I've recorded this with my phone just now, and this is the program we just wrote running. I'm switching from a completely green to a red to the image I converted previously, which is a pretty awfully drawn bumblebee queen. But there you go. That shows the basic principles of connecting up the FMC, connecting up the ILI9341 driver, and we can build on that in later videos, for example, adding in LVGL and so on. Thank you very much for watching this video. I hope it was useful, and I hope it showed you how you can use an STM32 microcontroller in combination with the FMC peripheral to connect up to a typical LCD display and an LCD display driver such as the ILI9341. If you liked the video, please leave a like, a comment if you have any questions, and don't forget to subscribe to stay up to date with any latest embedded systems, hardware design, PCB design videos, and more. Thanks again, and I hope to see you in the next video. Bye-bye.